Hello students, welcome to Sri Siddheshwar Women's College of Engineering Solapur. From the subject Engineering Mathematics 3, we are dealing with partial differential equations and applications. From this unit, we are dealing with the topic linear equations of first order. In the last lecture, we have solved two examples from this topic, linear equations of first order, that is Lagrange's linear equations. So before going to solve few more examples, just take a look what we have studied in this unit so far. First, we have seen what is mean by partial differential equation, then its order and degree, then how to form partial differential equation using two different methods, either by eliminating arbitrary constant or by eliminating arbitrary functions. Then we have seen the definition of partial differential equation of first order, and also we have seen the definition of linear partial differential equation of first order. In the last lecture, we have seen the form of Lagrange's linear equation. It is nothing but PP plus QQ equal to R, where capital PQR are functions of x, y and z. Now we are going to solve few more examples of Lagrange's linear equations. So let us see the first one. The question will be same. Solve the following PDEs. First example, x into y minus z p plus y into z minus x q equal to z into x minus y. So as usual, we have to compare this with the standard form and we have to identify capital PQR. With these capital PQR results, we are going to write Lagrange's auxiliary equations in three ratios form. Replacing PQR in this auxiliary equation, we get dx upon x into y minus z equal to dy upon y into z minus x equal to dz upon z into x minus y. Let us call this as equation 1. Now we have to use multipliers 1, 1, 1 in this equation 1 so that each ratio is equal to dx plus dy plus dz divided by xy minus xz plus yz minus xy plus xz minus yz. Here you can observe that the denominator of the ratio is equal to 0. So from this we can write dx plus dy plus dz equal to 0. Now we can integrate this result so as to get the first solution as x plus y plus z equal to c1, where c1 is constant of integration. We can call it as also a. So this is our first solution denoted by result number 2. Now we have to find one more solution. So let us consider the three ratios, that is the Lagrange's auxiliary equations one more time. Now we can rearrange these three ratios like dx upon x upon y minus z equal to dy upon y upon z minus x equal to dz by z upon x minus y. Now if you concentrate on these three denominators of result number 3, if we add these three denominators, we will get the answer as 0. So again using the multipliers as 1, 1, 1 to these three ratios from result 3, we can get one more solution. So these multipliers gives us each ratio equal to dx upon x plus dy upon y plus dz by z upon 0. So this gives us dx by x plus dy by y plus dz by z equal to 0. Integrating both the sides, we get log x plus log y plus log z equal to log c2. Applying laws of logarithm, LHS can be written as log of xyz equal to log c2. Taking antilog on both the sides, we get xyz equal to c2. We can call this as b, one more constant. So from result number 2 and 4, we can write the general solution of the given PDE as phi of AB equal to 0, that is phi of x plus y plus z and xyz equal to 0. So this is the required solution of the given partial differential equation. Now let us see one more example. This is very simple. We can easily identify capital PQR. Now write the auxiliary equations with these PQR results. So dx upon y square equal to dy upon minus xy equal to dz upon x into z minus 2y. Now consider first two ratios. Here both the denominators are having y, so y can be eliminated, and by cross multiplication we can write the ratios in variable separable form. So now integrating these equation we get minus x square by 2 equal to y square by 2 plus c1. Multiplying both sides by 2 we get x square plus y square equal to minus 2c1. We can call this as a. So this is our first solution. Now we have to try for one more solution. So consider the three ratios again. Now consider second and third ratio. Here it should be last two ratios. So again here x is a common factor which can get cancelled. So we get dy upon minus y equal to dz upon z minus 2y. By cross multiplication we can write z minus 2y into dy equal to minus y dz. On simplification we get y dz plus z dy minus 2y dy. These first two terms are nothing but derivative of yz, and this 2y term is nothing but derivative of y square. So we can write this as d of yz minus d of y square equal to 0. Integrating we get yz minus y square equal to c2, which is also called as b. So we got here second solution. Now we can write the general solution as phi of ab equal to 0, that is phi of x square plus y square and yz minus y square equal to 0. You can write this second term as y square minus yz. So you can write this solution as phi of x square plus y square comma y square minus yz equal to 0. So this is about the second example solution. One more example, y square into x plus y p plus x square into x plus y q equal to x square plus y square into z. This is somewhat different example as compared to previous examples. So just concentrate on the multipliers here to get the solution. The first part is very common, to identify PQR, to write the auxiliary equations, then to get the three ratios. Now consider first and second ratio. Here straight away you can cancel x plus y. It is common factor in both denominators. So we get x square dx equal to y square dy, variable separable form of differential equation. Integrating we get x cube by 3 minus y cube by 3 equal to c1. Multiplying both sides by 3 we can write x cube minus y cube equal to 3c1 equal to a. So this is the first solution. Now we have to check for the another solution. Here we are going to use different method which is not used in previous solutions. Just take a look. Now see, if we add first and second ratio and if we can equate it to third ratio, we get denominator of LHS as x plus y into x square plus y square. Here both the ratios are containing x square plus y square in multiplication form in the denominator, so we can cancel it. Dx plus dy upon x plus y equal to dz by z. Now we can easily integrate this to get the answer as log of x plus y equal to log z plus log c2. Now applying laws of logarithm, we get log of x plus y divided by z equal to log c2. Taking antilog, x plus y by z equal to c2 equal to some other constant b. So in this way, just by adding the two ratios and equating it to third ratio, we can have the solution. So this method is not used in any of the previous examples of this topic. Now we can write the general solution. Phi of AB equal to 0, that is phi of x cube minus y cube, x plus y whole divided by z equal to 0. So in this way we can try for different multipliers, different methods to get the Lagrange's linear equation solution. Here you should know the properties of equal ratios, laws of logarithm, integration results, and also the different forms of differential equations. So thank you for listening patiently. Have a nice day.